everybody. Thanks for joining us. We're really excited to have Kirsten and Simon from Humio here to present to you guys today. Humio are one of our strategic partners because we obviously believe in helping people build large scalable solutions, and we believe that log management enables and empowers simplicity and ease of use, and is a powerful tool for people who are building large and scalable solutions. And I think we're really excited to have them show the way that their solution can help the kind of developers solve the kind of problems we are passionate about. So excited to see what they have to say. Just a couple of housekeeping things. We will have Q&A at the end. So if you have a question, please use the go-to platform or tweet to us at Erlang Solutions and at Meet Humio. We'll be checking both platforms throughout, and any questions that can be used at the end, we will put to the team. Also, if you do find that your audio is not working at the start, there is along the top bar next to the window button, an audio button. Just double check that your audio output is your computer speaker. We often have people who were using headphones earlier in the day and they find they're not getting audio. So that's the best place to check. Without any further delays, I'll introduce Kirsten and Simon, who will take the presentation. Take it away, Kirsten.
Thank you. Yes, so I'm Kirsten, and I'm with Humio. We'll talk about log management today, and we have some demo of how it works with Elixir. Just really briefly, the guy on the top is me. I've been with Humio since it started. I've been engaged with the Erlang world. So some of you are probably connected to Erlang, given it's Erlang Solutions that's invited to this. So I did a lot of work on this Erlang virtual machine called Erlang. That was really just a toy project that kind of went out of hand. But a high-performance Java system. Nonetheless, I've been co-founder and CTO of TribeFork, which is a large consulting group in Northern Europe, mostly. So 5 years ago, I decided to sort of jump ship. I started as a subsidy of TribeFork and get back into tech. So I've been at it for the last 5 years, back in the trenches. So, Simon, maybe you could introduce yourself.
Yeah, hi, my name is Simon, and I work as a software and infrastructure engineer at Humio. Previously, I was CTO at a startup in Aarhus, Denmark, and there we built a system in Erlang. And I guess that's why I was so fortunate to get to build the demo that we're seeing today, due to my experience there. Yeah. And the demo we're going to see today is just like a simple chat system. It's not going to be incredibly scalable or anything, but given the power of Erlang, you could probably scale it pretty nicely. Yeah, that's me for now.
Super. So just also briefly, the agenda, I'm going to talk about, how Humio is a new approach to log storage and log management. We thought something new was really needed. And then I'm going to talk about some details of how we use brute force and how that actually outperforms traditional index systems, because this is a lot of the kind of misconceptions about storage systems that they need necessarily something that resembles a database needs to have an index. So that's maybe 25 minutes, hopefully. We'll try to stick to that. And then Simon will walk us through a demo of how it works and how to run it with an Erlang or Elixir system, and hopefully there's lots of interesting questions afterwards. So just briefly, to tell you we're a real company. This is just a slide that tells you that this is a real thing. We've been around for almost 5 years now. We're a bunch of kind of adults, bearded guys and women that have experience from already a long life of doing complex systems. We have customers, across the Western world. About 80 employees, 80 plus, I think, now in London, Aarhus, Denmark, and kind of a band across the US, both East and West Coast, and everywhere. And we got a good deal of funding from Excel and most recently Dell, but that's like 9 months ago. And we also have real customers that are using this for like large scale systems. So that's kind of credentials slide. So really, the reason why we started building, so this is the real talk, right? Really, the reason why we went into all this is when we're looking at software development today, we're sitting in these tranquil, quiet, nice office environments, or these days we're sitting at home in our sofa, and all the computers and all the action is going on somewhere else. So it's really difficult to get a good feel for what's going on in there. If you're, I like to say, if you're on a ship, you can almost feel the hum of the ship, like the boom, boom, the big engine that's pistons that are running. And if all of a sudden the engine stops, then it all feels unnatural. But when you're sitting in your couch, there's really no good way or easy way to get this sense of how is my system doing. And that's sort of the challenge that we really felt ourselves. And part of the reason for starting Humio, we've been using various kind of logging solutions, and we definitely saw the potential in using logging as kind of the pulse of the system, and drive data out of that to give us alerts and dashboards and understand what's going on in the system. But there's a lot of shortfalls in these systems. Either they were way too expensive, they didn't provide live access to data, they couldn't deal with volume, a lot of different things. So if you look to other professions than computer science, let's see, I need to click here. Oh, I thought I had, yeah. This is sort of the thing you see, right? This like this rugged launch in late 60s, where on the top of the screen you have some dashboards that's sort of kind of high-level view of what's going on. You can look at those and see, that looks normal. Right? You know what you're talking about, of course, if you're used to looking at those dashboards. And then if something is not normal, you can go to one of these guys and ask, so could you please kind of dig into the details for me and tell me why is that thing weird? So this kind of two-way split of observing a system that's far away and has lots of moving pieces is sort of a proven approach. And it's very much the same thing you can do with logging, where logging and the log stream is sort of the sensors, and you can drive all sorts of interesting data out of that. So really, Humio is that's the box in the middle. It's a combination of log aggregation, so it makes it convenient and easy to pull all this data together, and an analytics platform that lets you deal with computing stuff in real time or ad hoc for old data, essentially for two use cases. So the first use case is all this metrics and monitoring stuff where you want to deal with data live. Stuff where you want to know exactly right away when it happens. You want to see it on a graph or get a message on your phone or be alerted. So that's one aspect. And the other aspect that you use Humio for is just like a search engine. Is drill down, log search, typically in the scenario where something bad happened, and you want to go back and see what really did happen, and did this happen before, and maybe this is a new thing that we've never seen before. And so we set out to build one of the a system like this with these kind of most systems in this observability space is either a metric system or a logging system. But since the kind of the sensor data that we have for a distributed system is these logs, it's really convenient to drive both of these use cases, because then you can also cross-reference them and etc. And one of the areas, interestingly enough, we started out to build this as a DevOps tool for software developers, because we were software developers ourselves. But it turns out that the security space, they've sort of been doing this already, and they already realized the value of kind of big data log analytics. So one of our first customers, this was a healthcare organization. It's kind of very much the same diagram. We took live data from 30,000 PCs, some various server infrastructures, and network data, network monitoring. And this is really high volume, like 1 million events a second, 20 terabytes a day. They used this, they deployed this like the week before that Trojan Petrolia or something like that came out in December 17, and they were so happy to have this actually for shifting through files and figuring out what was going on. So back then, this was seriously pushing the system to its limit. Today, we have customers that go beyond this. So kind of the laundry list for the system we wanted to build was kind of a combination of these things. So this is kind of the design space we set out to solve. First of all, you want to be able to record everything, and that's because you never know what you want to search for. So kind of bullet 3, you want to be able to look for unknowns. Something happened that hasn't happened before. That's typically the case when things go wrong. So systems where you have to set up an index and decide up front, I want to keep track of these pieces of information and put them into these columns, often fall short when something happens that you didn't expect. And so often we've seen that it's super valuable to just have like free text search access to historic data. Then we really like the idea of being able to do this in real time, have access to drive metrics, computed metrics, metrics that are pulled out of the logs in real time. So something as simple as just a live graph that shows how many errors per minute do we have right now is a very good place to start, because large systems tend to have errors. I mean, in the Erlang world, it might be process failures or restarts or whatever that you want to show. We also built it from day one to be installed on-prem, and that meant the architecture was really designed to be relatively easy to put on-prem, because at least the first dozen customers were exactly in healthcare and in security, and we also came from a context where we built financial fintech solutions, and so having this is part of the product. A lot of new products, a lot of products in this space are cloud only or SaaS only. So having something customers can install, that actually narrows down the competition to just very few. And then, of course, we wanted it to be affordable, in terms of how much hardware you have to throw at it, what we sell our licenses for, and how easy it is to operate. So this combination of things really became, the mission we were driving for. And before Humio, there's been nothing really that fit this particular laundry list. And that's really the mission. We're out to change the way people log, because we've seen ourselves an enormous value from this in the DevOps world. And it turns out we realized security people knew this beforehand, But most of the solutions in the security space were like way too expensive. So we're seeing a huge uptake. A lot of new customers come in from the security realm today. Okay, so so the obvious thing to do when you build a solution like this is to put your data into kind of this broad category, an indexing database, a database where you say, I want to be able to search for these things, or you build a free text index. But they're really built are kind of the basic trade-off in a system like this is to deal with low volume ingest, and that's where all the hard work is, and then have a high frequency of searching and searches. And that's not exactly the use case in a logging solution. In a logging solution, you would have lots of data coming in, and actually you would only look at the data whenever there was an issue. So it would be quite the opposite. So when you build an index, it's very much like, it's very much like a physical index. And this, if you're not a native English speaker, stuff like mice and windows, they're real things. Indexes are real things. You realize that? And an index takes up space. It takes time to manage and set up. As the data arrives, you imagine it's a library, put in books, and every time you put in a new book, a new log line, you have to figure out where to index it, where's index card, etc. There's a lot of work in that. You also need to store the data, of course. You need some shelves to store the data on. And often it's the case in these systems that if you want to be able to search for more than one aspect or angle or perspective, you need lots of indexes, and you'll have systems where the index, cross-reference index, takes up way more space than the actual data. And this is what we wanted to avoid, right? Because if you're logging everything, then you don't want the index of everything to be 6 times as big as the everything itself. Another development that is happening is really, I've used this quote in other talks. If you've seen me in Erlang world before, it really is quite amazing that the most amazing achievement of computer software industry is its continuing and cancellation of steady and staggering gains of the computer hardware industry. We just keep wasting cycles and we keep wasting hardware. Sometimes, at least when you're in product mode and not consulting solution mode, it really pays off to actually go that extra bit and do the real engineering that it takes to do it. And that's what we've done in this case. So the other thing, so when index-free store, which is what we pride ourselves on, is actually a system that really, you heard this discussion before with NoSQL stores and how React works, for instance. It's really a data store designed for high volume ingest. And then we shift or do a trade-off, shift the work to when we're doing queries. And this is like what's so counterintuitive when we try to explain how this is fast. So the way it works is very simply, we have these large files we call segments, and then we have a very, very light set of metadata, sort of tiny index that actually fits in memory, even for huge systems. That means we know kind of roughly what's in these segment files. And then when a query comes along, we can use this metadata to decide which segments to do brute force searching. And the way this works is, I had this suspicion that I jumped over a slide. Let me just, so the other thing, development that happened broadly in analytics is streaming engines and streaming data processing has become commonplace. And this has been popularized by a range of open source tools that essentially do parallel MapReduce to do analytics. And that's a really ideal platform for doing high volume data processing in real time. So it's a Humio is a combination. We have our own streaming parallel analytics engine, and then the store that is used for ad hoc queries on historic data. So the way reading from the way we do make this brute force stuff really fast is, say, if you want to run grep on 1 GB of data, how much time does that take to do? Well, on a normal machine, you would spend 1 second reading the data in, and then maybe 100 milliseconds actually doing the search to do like full free text search on a gigabyte of data. If you compress the data, you can reduce that. You can reduce that work. So the I/O wait, or waiting for the disk to load the data, is maybe 1/10, say 100 milliseconds to load the data. Then maybe 500 milliseconds in this case to actually do the decompress and then do the search. We're already almost twice as fast. Plus, we're saving a lot of disk space. It's clearly. So in Humio, we're typically compressing logs between 10 and 20x on real logs. So that's quite a big difference from loading up your data by 5, 6x if you have these huge indexes. So this can easily become a 100x in terms of how much disk space you need, compared to putting in a system that has classical indexes. So now, as Erlangers, you would know this is trivially parallelizable, right? We can run this in 4 parallel tasks if we have 4 cores, or even more if we have more. So a Humio system is really ideal if you have a fairly large system, if you have more than 4. If you have a cluster or a shared multi-tenant system where you could first, for 10 milliseconds can get the entire cluster's data processing. That's kind of the ideal setup. So it's everything in Humio is trivially parallelizable in the way we do MapReduce. Of course, there's communications overhead as well, so there's a limit to how far you can do that. But say you split it in 4, then we're down to 0.2 seconds. This, if you're intimate with Erlang, scheduling of I/O and waits makes a huge difference, and we'll get to that. But if you look at, if you take a quarter of this data, of this gigabyte of data, decompress it, so it fills 256 megs in memory, then you definitely thrash the caches of your CPUs, right? So you might have decompressed all the way through the data, and it's in main memory, but you haven't exploited kind of really the caches of your CPUs. If you instead split it up into tiny little, it's jumping twice every time. If you see the development from here to here, you split it up into tiny little chunks of data that you can decompress on the CPU core, then you get this advantage that you actually save bandwidth in between the CPU and main memory. You don't have to spill the data back out to main memory, and it's incredible. We chunk up the logs in little chunks that actually fit when they're decompressed. They fit on the CPU core, and that means you get an order of magnitude more speed in actually processing and doing a search. Now, of course, in many cases, this compressed data will, if you just searched it before, say, or you just wrote it a couple of minutes ago, it might still be sitting in the operating system's file cache. So in that case, I'm jumping 2 slides at a time. I'm really sorry. It's happening so fast here. I don't. Right. We squeezed it even further. We squeezed the full 100 milliseconds further off. So this is a huge difference. So by kind of careful engineering all the way down, we can actually make brute force search like incredibly fast. And there's so a lot of people also have realized this. You'll find lots of blogs around how to do this. And it's not like you don't need CPU or special configurations for your CPUs in any ways. It's really about thinking about your data structures and how you organize the computation. So when you do a search in an index-free system, we generally have these different levels. So we'll have, as data arrives, or when you do a search, you'll typically search for a time frame. Well, let's say you have a 5 terabyte a day system, and you want retention for half a year. That's roughly a petabyte of data you're storing in your system. So often you don't want to search for everything that happened in your entire half year. You might just want to search for what happened 2 days last week. That's a 100x reduction. Then when you're in this scale system, tags, which are like attributes that you associate with your logs. It could be server names or it could be services names. Typically can also reduce your search space by 100x. We have some Bloom filters that take up about 5% of the storage of the actual raw data. And then at that point, we can, we're down to 3 times 100x of the IO needed. So kind of the whole trick in this is reducing the number of these segment files that we need to brute force our way through. And that's really what makes this kind of index-free system fast. So you could say there is sort of an index. Yeah, we have more like a directory, an index of very large files that each have typically on the order of a gigabyte of data. So Humio is this combination of index-free search, where we shift the CPU load to query time, data compression that we use for ad hoc queries. It does require kind of rewriting the entire stack to make it fast. And the other side of the equation is then combining this with the stream processing engine, where we use the same query language. So it's like very easy to move from one to the other. There we process data when it's in memory anyway. This is really good for, say, the opposite of ad hoc queries. They're upfront defined queries, things you know you want to look for. And this is what services dashboards and that. So you'll see this in the demo, this difference between these things. I think this is a good time. We've spent short of half an hour. Maybe here we go. So Simon, maybe you could just talk a little bit about what you do in your demo here.
Yeah, so as I mentioned in the beginning, it's just a simple chat system. And to update the UI, I'm using something called Phoenix Live View. I don't know if you guys are familiar with it. It's a pretty neat way to have a live UI as a web UI, where you actually sending basically the diffs of the data needed to render the UI in the front end. So you don't have like a big JavaScript framework that you use to render things with, like React. Instead, you actually just basically do what is similar to a server-side rendering with a templating language, and then it calculates the difference from one push to the next, and it sends the difference, and then it patches it on the client. So that's pretty neat. But it's viewable through a browser, obviously, and that connects with a WebSocket to the Elixir server. And here we are running a live view channel, which is what the WebSocket connects to. And that channel is connected to another process, which is like a chat topic where you can send messages to, and you can see which users are connected. And then we also have some chat bots which will act as regular users and send messages to the chat. And in addition to that, obviously a bunch of different processes, but worth mentioning is the metrics puller, which will periodically collect information about both the VM and each of the processes running in the Elixir server, and then ship off that data to Humio. The shipping of the data is just done by logging to standard out. So both the logs and the metrics are just printed to standard out. And then we use a log shipper called Vector to take the standard in and ship that up using HTTPS to Humio. And in Humio, a lot of magic and secret sauce happens. And that's what makes your logs and metrics show up. And that's like an overview of the flow of the data in the system. And when I can share my screen, I'll start showing the demo. So as you might have noticed, I actually, the code is available on GitHub if you want to like play around with it afterwards. So to start with, let's just take a look at the actual interface. So it's just like a very simple chat system. Hello, we can write, and it obviously arrived down here, and Mrs. Humio can reply hello to. And obviously, this being a live demo, we already have some trouble. I'm not sure exactly what's going on here, so let's just see exactly what's happening. Okay, now everything is working by magic. I don't know. You can like join different channels and communicate through those. And if you're not in the channel, you don't have that, so you can see it. And taking a look at the code, just briefly, it's pretty standard, just Erlang or Elixir project, and we just use the different building blocks of Erlang to build the chat store and the bot. So the chat store is just using something called an agent in Elixir to store the state of the chat, and we have different functions in order to update the data. So if I add a message, it will update the data of the agent, adding a message from this user, and so on. Similarly, the bot is done using a gen server, actually, which is very similar to an agent, and an agent is a gen server. It's just like with a nice API for just doing data stuff. And the gen server have a different kind of functions for starting, well, different bots. And the Phoenix live view thing, it's located in here, where you have this page live, which is the channel process. It's called a live view process, and it has a bunch of different callbacks that it has to basically set up the page. So on mount, that means that's when the page is first loaded. If you're connected to the socket, so that means that if it's on the second render, basically, because mount is called immediately, and then it's rendered on the server, and then it's sent back, so it's server-side rendering, and then afterwards mount is called again when the socket connects. And in that case, we subscribe to a pub sub, which is running in the background, in order to receive the messages from the chat store. So each of the chat channels are running as a separate process in these chat store processes. Yeah, and then there's like a bunch of different stuff. that is like implementation specific. You can look at afterwards, or if we have time. So I mentioned that we were shipping using Vector, and it's this thing. It's available from vector.dev. And in order to ship the data to Humio, you need a ingest token. So if you want to try that out afterwards, so if you want to try around it with your own stuff, you can just create an account at Humio Cloud, and then you have a sandbox repo that you can use to just ingest data. And there you can set up a, I can just go and show you. You can set up a API token, which is used to ingest data. You just create it here. Then you can see the ingest token, and you can then copy it. And then what you do is you can use this configuration file for Vector, and then you just paste the token here, or you use an environment variable, and then you can just pipe the output of your server or your process into Vector, and it will ship it off to Humio. So in order to get the data from Vector into Humio and have it nice and searchable in Humio, we do a bit of parsing on the way in. And so I have a parser here, which is a parser which is written in basically the query language of Humio. So you have like the full power of the regular query language at your fingertips when you want to parse stuff. So in this case, I actually just received some JSON from Vector, and I pass it up twice because the actual raw string is JSON, then it's packaged inside the message attribute called message, and in there it's also JSON. So that's why I have these two parsed JSONs twice. Then I parse the timestamp, which is received here, and I note that even though it's actually supposed to be UTC, for whatever reason, I'm actually getting my local time, which is Europe Copenhagen. So I can specify that I'm actually using this time zone, even though it's reportedly UTC. Then Humio will make sure to do the correct time adjustments. Then I drop the field time, and I rename severity to level because I like log level better. And then what I do is I do a case on some of the input data. So as you can see over here, this is a way you can test your passes. And when you, so you can run your tests, and when you do that, you can see how does the parser take the raw data and put it into different fields. So this could be thought of a bit like indexing, but it's not really. It's just a way to segment the data. So when we run through it very fast, we are able to look into each field very quickly. But it's not that there is an index. It's just how the data it's stored on disk. So in the case of us finding a metric true, that's because all our metrics has an additional like formatting, which is like key value paired. So we can just say that, okay, in the case that we find metric equal to true, we pass the message with a key value parser, which means that in this case, we get these different things, the process info, the type, and so on. Those also becomes fields in the data structure. Then if we take a look at some of the data that we're ingesting, it's mostly metrics right now, because as I mentioned, we had this metrics poller that is just every 10 seconds scraping some data off the Beam VM and shipping off. And so we can say if we don't want to look at that, we might want to not look at the raw string because it's not exactly easy to take a look at. So what we can do is we can use the Humio UI to say remove the raw string, and then take each one of these fields and say, okay, I actually want to look at the message. And for these, I don't actually want to look at those metrics because I don't care so much about actually looking at the metrics for each of them. I want to look at them aggregated. So now that I deselected metrics, I can look at the actual logs that is shipped, And as you can see, we got some messages here when I posted a message. So if I just gonna turn it down to a minute, and then let's see if we get some data through. See here, oh, someone wrote it here, yeah, and we got a message posted. So we can see that the message went through and there was a log line, and we get a different kinds of metadata about what's the file that was locking this, what's the function that was locking this. So it's obviously very good for debugging. We have information about what's the PID of the process actually running the chat channel, and what's the PID of the client process. So in this case, this will be that the process that is running in the Phoenix live view channel. Yeah. So if we take a look at some of the dashboards that I built, or the dashboard that I built, you can see here that we had just a message that just got in, and so we have 4 different widgets. We have one which will tell me if the message queue is or what the value of the message queue in each of the processes are, and also how many messages are so chat messages are throwing through the system. And we have something that will just tell me what is the average total heap size for each of the different processes in the system. So you can see I have different chat stores and I have bots and so on that are reporting data. So in order to get a bit more throughput, we could add some bots, but first I want to actually adjust this thing, because so it would be nice if this torque thing was actually the same as this. So if we could directly compare these things, so it's set the same. But the problem is that the message, the data that we are looking at here don't actually contain this information. And we can improve on that by using a join to extract that information. So Humio has the capability to join different log streams and then take data for both of these streams and combine them. So if you have one query that gives you one set of results and you have another query that gives you another set of results, you can take the fields from the second set of results and basically merge them into the events of the queries for the events from the first set of results. So if I go into this, so you can see this is really easy. It's just a query which says message posted, and then I pipe it into time chart, and I say make a series for each of the metadata topic fields. So in this case, we only had something from talk in this case. If I go in and go into dev and I write hello again, then shortly this should pop up. There we go. We see dev showing. So if we wanted to have this represented as this in the same format that we had the other chart, we have a couple of different things we need to adjust. First of all, the way that each of these different log lines are reporting the PID is not actually identical, just due to a configuration error in our system. So what do we do now in a live running system to correct this? Well, Humio has some pretty nice regex capabilities to basically take and extracting new fields out of the raw data. So just to cut down on time spent, I'm gonna check out the query that I want it to actually be, which is a save query, which I have in here. So you can save queries and run them later. And we have this query, so where instead of just saying message posted, we do a bit of data processing. So first we do a regex over the event. So in this case, that's over the message text, and we say if you can find something that starts with bang hash. Oh, I can't remember, hashtag or whatever it's called, PID, and then you can extract whatever comes after that. And we do that from the field channel.pid. So if we look at the original query, we can go in and see the events here, and we can see that we have this this PID right here, channel PID. So that's what we're doing in here. We're saying, look at that field and then do this regex on the data of that field. Then when we have this, we have the PID, then we can join on a new query, and then we're actually just searching through all the data. And we're saying, okay, I have a field called PID, and in the other set of data, I want to look for logs lines that have a key or have a field also called PID. These could be different, but in this case, it's PID both. This PID is based on that name. So if I call this PID with 2 Ds, I would have to call this PID with 2 Ds too. So that's the way they join it. It's similar to a SQL join. And then I specify that I want to include the field registered name from the subquery, as we call them, and basically add that onto the primary query of the message posted query. And then after that, I get the registered name. I do a bit of string replacing in order to make it look nice. And then I can take this thing and go into my dashboard. Where was it? I think I had it here. And I can edit it. And then I can do this. So I take the query, and then we should get the same. And see, since I didn't change it here, we still have the field of metadata topic, but now we have the new one called registered name. And we can do this. So that's just showing how you can use different types of functions in Humio to extract data and to join it, even though that the data that you wanted was available in another query. So we can save this and return to the dashboard, and now they actually are similar. Yeah. So
Right.
let's see.
Yeah, I think, I mean, what can we ask the control tower here? How are we doing in time? Was it supposed to end quarter past, or?
I think it's fine to keep going. Yeah, it's not a hard deadline.
Okay.
Okay.
So I'm gonna add a few bots into the system, and some of you might recognize some of these names and what they're writing, and they are just starting to write in the dev channel, and you'll see immediately the throughput of the dev channel starts going up because we have much more bots starting to write. And what we want to do now is to like simulate a problem with our system. So in this case, let's say that we stored all of the messages, we stored them in a database somewhere. Well, maybe that database slowed down, so each of the messages starts to take a delay. And we can do that down here. This is just like a remote shell into the running Phoenix system that I have. So we're just going to add a message delay to the dev channel. And we're going to put a message delay of 1200 to, let's say, 1800 milliseconds. So it's going to vary a bit. So what we will see is like the throughput will probably go down a bit because each of the messages now have to wait around 1 to almost 2 seconds before they are posted. And hopefully what we will see is that the message queue will start to build up. And if not, that's simply just because that the system can actually keep up. So let's see if, oh yeah, there we got the first one. So we can see that dev actually has a message queue of 2. So that means that the process couldn't keep up with the amount of chat messages coming into the system. So this is obviously something you want to like monitor if you have a chat system is can my chats keep up with the amount of data trying to be pushed into them. And down here we have something where we can see if we have restarts of a gen servers, and we actually had one, and we can see that the Rapid bot actually restarted. And the reason for that is that when you try, as a default, when you try to send a message to a process in Erlang, as you probably know, there's a timeout of 5 seconds. And if that timeout is expired, you will an error will be thrown by the Erlang system, and the process will crash and then will be restarted by its supervisor. So that's what's happening here. And probably we could, because I didn't really do a lot of defensive programming here, which you obviously often don't really need to do in Erlang, but I didn't even set up like an increase in the amount of times that the supervisor will restart the processes. So if I just start spamming out messages here, it's likely that a lot of more stuff will start crashing. So let's try adding 10 spammers that just write a lot of stuff into the channel. See if more stuff might start crashing. It looks like no messages is coming through really right now. Let's see if we join dev down here, if we're able to get it to run. It looks like the spammers were not even able to actually start up, because as part of starting the spammers, they are trying to join the chat room, but because it's already like challenged due to the delay in the message delivery, the message queue builds up and it's unable to join, and then it will just start crashing. So you can see here we have a number of these spammers which are crashing. And that's pretty much all for the demo. And if you wanted to, you could set up alerts for these things. So you could say, based on the query language of Humio, you can build up a query that just says, if my message queue length is larger than, say, 10, throw out an alert, and you can then push that to Slack or a webhook or whatever you want to use PagerDuty, and then you're woken up and you need to look at the system. Yep, that's it for the demo.
Perfect. Thank
Keep
you.
it on. Yeah, all this stuff that's happening here is all happening in the stream query processing, right? These are all live queries.
Yes,
that are being processed as data arrives, right? So this is basically, it's just continuously computing these using a window function, what is happening in each of these time slices, and just so the data that represents these graphs is just kept in memory and continuously updated as data arrives in Humio. Yeah.
Cool.
Very nice.
Perfect. Thank you so much, both of you, for the demonstration and also the presentation earlier before that. We will open up to question and answer. So either via Twitter or on the GoTo platform, send us your questions and we will put them to the team. The first one we've got in is, to what extent is it necessary or even just helpful to enforce a standardized log record layout?
Well, it's not necessary. You can just put your data in, and it'll show up as whatever it is. There's full, very fast free text search. So there's no necessity to do it, and that's really convenient because often a real system is a mix of different kinds of logs. Let me turn on my camera again here. In a large system, though, you often also want to standardize it somewhat. You could do that to some extent, of course, in your application logs, or you could do that as Simon was showing by rewriting the logs as they arrive to get some standardized attributes. So it's convenient to have things that are the same to be sort of named the same, because then it's easier to align them, to join them. So if there's a notion of say source IP, it's convenient that's called the same. But often in a large system, what happens is you have so many different sources of logs. They're not all just Erlang logs or lecture logs like this. They're database logs. They're logs from your web front server. They're logs from various subsystems, and might very well look different. So typically we see that you kind of do these adjustments kind of per presentation, because so when I'm doing this presentation, just like Simon was showing, when I'm doing this presentation and I need to combine this data with that data, I'll just do a regex extraction for exactly that data and make sure the attributes map up. So there is no notion of a schema, right? Each log entry is really just a little dictionary, but there's no schema enforced. So, and there's also no the dictionary is just string to string. So the fact that some certain things are numbers, they're just represented as strings internally. Yeah. Another question?
Sure. Does Humio support windowed, aka time series type queries?
So it the whole kind of data store is a time series database in the sense that the core data type is a timestamp and a blob and a dictionary. It's a timestamp and a dictionary that's string to string. So everything is centered around time ranges. So as you see, the windowing functions in the live data that we saw on the dashboards, and also when you do historic searches, kind of the core, or almost the only index we have is for these segment files, what is the time range of data in each of those? So that maps exactly. So yeah, so the short answer to that is very much so, yes. Time is essential. So we have two concepts of time. There's the event timestamp that's typically extracted from the event, and then the arrival timestamp. When Humio sees it the first time, that's what we call the ingest timestamp. So often those two can skew if you have data that was produced earlier and arrived late, if the source of the data was offline, for instance. In security systems, that could be, an endpoint security logs that come from a laptop that was offline. When you get online, you get logs of what happened last week, and you might want to set up queries that deal with those two in separate ways. Yeah.
Perfect. This one came through when you were describing in the first half of your presentation the way the data is stored down into chunks. The question is the data stored in these chunks, or is the chunking done during the runtime?
So the data is, so as data arrives, we basically keep, we have a buffer of data that we're about to write to disk, and we build up these segments. So it is stored. It is stored in these chunks, and we build up somewhere in or less than a megabyte of data, because that's what fit on level 3 cache, and then that's a chunk or block, we also call it, and then we append that to files. So the core segment file is kind of an append-only file where we append these chunks around a megabyte at a time, so that's a megabyte before it's compressed. So that typically turns into 100K or something like that. And then every time we hit that, we append that to the segment file. There's a little more detailed than that, but that's the general idea. It's very similar to how Kafka works. If Kafka was always chunking in 1 megabyte sizes. Yeah.
Perfect. What database is being used? Is it SQL or some no SQL?
So we build our own database for this. So it is Humio is the database that we're using, and it so it's optimized for this exact use case. So there is no other database than Humio underneath. It is this data store, this time series engine that we built, and that's it's perfectly optimized for this particular use case. And yeah,
That is really cool. This question is, does your approach to brute force search have any restrictions?
there are there's certain operations. So when you run an aggregate operation, that some of those need to carry along a sizable state. So the way it works, say you're computing the average of some number, right? You could run that as a distributed query, and on every local node or every local CPU, you keep track of a count and a sum of the values that you see. That can run completely distributed. You can pull those together and add up all the counts and add up all the sums, and then do the division there to compute the overall average. And the same principle is used across all the aggregate operators that we support. And some of these aggregate operators are approximate because that's, say if you do count distinct, for instance. If you do a count distinct, you would really have to keep the list of all the distinct values you've seen, bring all those together, and then do the big count of the distinct values. So that's done with an approximation called HyperLog Plus, which is based on an assumption that you have a perfect hash function, and then you can do some bit magic. So there is some of these aggregate operators that are approximate, and some. So HyperLog log is not so bad. There's some that are worse in terms of the amount of memory, even though it's a kind of this approximation of huge space, they still need to kind of carry around a fairly large state, and there's some limits on the sizes of things you can do. So, for instance, the group by operator, which is an exact kind of dictionary abstraction, essentially it's just a hash table internally. There's a limit to how many elements we support in a group by. And that's configurable, and I think defaults to 20,000. If you have lots of memory, you can increase that if you run your own installation. So there's these operators. They have some kinks and tweaks and aspects that are limitations. So yeah. They do have some limitations, but that's if you're running through 50 terabytes of data and want to do a compute distinct, you need to do some. You can't just bring all that data together. So this is it's a really interesting discipline in kind of streaming aggregate operators that has really evolved over the last 5 years because these streaming query engines became popular. So we re-implemented our own versions of all these to fit into the Humio engine and framework. But that's actually quite interesting reading if you want to read into kind of streaming aggregate operators. This is something that Yahoo has done, for instance, a whole lot of work in for the benefit of Hadoop systems. There's been a whole bunch of research, likewise, around Apache Spark for doing these streaming aggregate operators, and we're basically just basing on that research space to do these computations, and that's as I see it, that's industry kind of standard algorithms. Of course, there are tweaks and optimizations we can do to make things run better in context of our system. It's and all the performance. It's interesting along the way here. When we do profiling to optimize Humio, we actually focus on the one metric that really is what we optimize for is reducing allocations, because it's all built. Humio is built on Java, on the JVM, with various JVM languages. But the fact that garbage collection is ultimately kind of common shared bottleneck, unlike in Erlang systems. Actually, on large-scale systems, the primary performance metric is how many allocations does something do. If we can reduce allocations, it generally increases both performance and scalability. That's because as long as you can keep data structures small and work on core, it almost doesn't matter how many operations or copying you need to do if you don't need to allocate memory and then later deallocate that indirectly through garbage collection. So we've taken a lot of these things and rewritten them so they do a lot less allocation. Yeah.
That's really cool. I think we have time for probably two more. One is, you mentioned during the talk that you could push alerts through to Slack or webhooks. Is the webhook option done via Humio or Live View? What alert features are available in Humio?
So all our alerting is currently based on webhooks. So it's Humio server that kind of calls out to webhook. It can go through, in enterprise settings with various proxies or gateways or to authenticate, because it's not nice if random servers are talking directly to outside systems. So kind of at technical level. The alerts are really just webhooks, and you can, we have a standard configuration. There's some email servers that I think we actually also take, we can also send SMTP directly. You can configure them for SMTP. So typically what customers do to do more advanced stuff there is set up a little web server where they can control shell script or whatever, another service that does more comprehensive actions in response to an alert. The alerting mechanism in Humio now wasn't shown, and that would be too complex to start talking about now. But really, that is also just the core idea is you write a query which is such that if anything comes out, you want to know. Right? So you say, show me, count all the errors, and then you filter out, say if the errors is less than 4, if the count is less than 4, and then you write the query so that nothing comes out of that. So you only get the list of errors if there's more than 4. So you can write a Humio query like that. And then if that happens, we commit that list. And that runs in a windowing function, again, just like you saw on the line. So that's an area where we are also doing actually a revamp of the implementation of some of these systems right now, because we've had a lot of feature requests in enhancements and new things to doing that. There's one of the new things we're coming with are these kind of timed alerts that run on a schedule, or scheduled alerts. So instead of just constantly keeping like a running window and looking for, is there say four errors or restarts or whatever within a time window, you can also run it at a schedule every hour, every day. And that can help you make sure that you only see each error once. Some of the security context, it's nice to not have the consequence be immediately after something happens. So if you're looking after a bad guy, you don't want to give him that information, that signal that when you do this, I do that. You want to kind of put that on a separate schedule. So maybe actually only check it once every 5 minutes if something did something bad. So it's not as easy to kind of reverse engineer what security operators are trying to fix. So this is an area where we're doing, especially for security use cases, but that kind of falls over to DevOps as well. Stuff that do there. So we out of the box, we have integrations to Slack, email of various kinds of providers. There is integrations to these Ops Genie, these types of issue or event monitoring services, PagerDuty and such. So we don't have very complex mechanism for doing coalescing. So this is not a new PagerDuty. We kind of explicitly are out of that. The problems of coalescing lots of events that is not dealt with in Humio. You would, for a large-scale system, you would probably still want the PagerDuty or Ops Genie or something like that to deal with who's on call and coalescing series of events into one by rules, etc. We're not right now, at least, trying to solve those problems. Okay.
Absolutely perfect. And one last question, and obviously a question that shows the success of the presentation, I'm sure. Is Humio suitable for other languages than Erlang and Elixir? What other systems is it compatible with?
Anything. Anything that anything that can send out text. So that's pretty much kind of the design idea is the lowest common denominator of all these systems that ship logs is just some text, typically with timestamps in them. So that's large scale, just host logs from syslogs, for instance. We have various application logs of all kinds, Kubernetes logs. It is networking. We kind of have set up all kinds of network monitoring logs so it should be Cisco logs or other kinds of data streams that describe network transactions. We have support for all these firewalls that emit logs. So there's a handful of native protocols that we support in terms of how we receive it. So it could be syslog or individual UDP messages that we can just treat as text. Continuous TCP stream that will split into events by new line. So really it's completely free form. And then there are some of these more structured protocols that we support for receiving data that are generally HTTP requests that send JSON structured data. And there is a couple of different protocols for how that can be delivered. And basically, that's the first question on the front page of if you go to docs.humio.com, you'll see the integrations, which is really a question of, the first question is the different kinds of data, ways we can receive data. So, but anything that produces text with the timestamp is perfectly suited for Humio. So it's not general relational data, for instance. It's typically something that represents events. Okay.
Perfect. Thank you, everyone, for joining us. Thank you, Kristen and Simon, for presenting with us. It's been really great to have you all. Just as a bit of housekeeping to end the day, the email we will send out to you early next week will have the recording of this so you can watch back, clarify anything. If you are looking to contact us at Erlang Solutions about anything, you can do so on Twitter, Facebook, at Erlang Solutions, LinkedIn, all the major platforms. Please get in touch. We're always happy to help. Humio, at Meet Humio is Humio's Twitter account. Again, they're always happy to help also, so feel free to get in touch with them. In the email, we'll also include details on ElixirConf EU Virtual, which is happening in early October, and our next webinar, which is about how learning Elixir can make you a better Java programmer. Thank you all for joining us. Have a lovely evening.